Welcome to the 20th lecture on the course Advanced Steel Design. In this lecture, we are going to do more examples on shape factor. In the last lecture, we already said that shape factor is expressed as MP by ME, which is ZY sigma y ZP sigma y ZE, and therefore, it is actually the ratio of section moduli of plastic to elastic. So, on this example, we applied and worked out a rectangular section, and we found for a rectangular section we got the shape factor as 1.5. Okay, we derived that. Now, we will derive furthermore for different cross sections. Let us take a circular cross section as you see on the screen. Okay. The radius is R. So, let us say this is classical example B, a solid circular cross section, radius is R, and we know the center of this particular part will be 4R by 3 pi as you see here. Okay. The standard expression which we know. So, let us say the upper half is A1 and lower half is A2. Let us say A1 is pi r square by 2, half of the area, which is also equal to A by 2, because you know this is actually equal area axis, correct. And if I say this as y bar 1 and this as y bar 2, we know y bar 1 is 4r by 3 pi, which is also same as y bar 2, where r is the radius of the solid cross section. So, we already have an expression for ZP, section modulus plastic, which is A by 2 y bar 1 plus y bar 2. Let us substitute that here. A is pi r square by 2 okay, that is A1, y bar 1 4r by 3 pi plus y bar 2 4r by 3 pi, which I will get this value as 4r cube by 3 pi. Okay. Let us find out the elastic section modulus for this, which is I by y max. So, which will be pi d power 4 by 64 divided by d by 2, which will be pi d cube by 32, which can be expressed as pi 2r the whole cube by 32, which will be pi r cube by 4. So, as a classical definition, shape factor is Zp by Ze, which is 4r cube by 3 pi divided by pi r cube 4. Okay. So, which will become 16 by 3 pi. So, this is only 4r cube by 3, sorry. Okay. Please make that correction. 4r cube by 3, as pi goes away here, right? Pi goes away here. So, 16 by 3 pi, which can be 1.70. So, that is my shape factor for a solid circular bar. Okay. Having said this, Let us do one more example, which we will do it now for an annular ring, a tubeless section. Okay, let us say a tubeless section. You know the outer radius is R1 and the inner is R2. So, obviously R2 minus R1 will be the thickness of the tube, okay, which is T. Let the upper centroid be at y bar 1 from the equilibria axis and the bottom centroid be y2, and we call this as A1 and this as A2. So, from the figure you can very well easily calculate A1 will be equal to A2, which will be pi r square 1 pi r2 square by 2, which can be pi by 2 of r1 square minus r2 square. We will also know y bar 1, which is also equal to y bar 2, which is a y bar by sigma I. Let us do this way, sigma a y bar by sigma I. We will employ this equation. So, let us try to find out. So, I am taking a semicircle, okay. So, this has got two areas. So, this one is separate and this one is separate. We know this is at the radius r1 and this is at the radius r2, okay. So, with the help of this we will employ this equation and we will calculate this. Y bar 1, which is as same as y bar 2, will be, let us say, pi r1 square by 2, half of the upper area, the black one, okay, and the centroid of that will be 4 r1 by 3 pi, okay, minus pi r2 square by 2 of 4 r2 by 3 pi. Am I right? So, that is sigma a y bar. Sigma a r1 square minus r2 square pi by 2, okay, which we simplify will be 4 r1 cube by 3 pi minus 4 r2 cube by 3 pi divided by, okay, let me write it this way. I will write it here, okay. Y bar 1, y bar 2 will be 4 r1 cube by 3 pi minus 4 r2 cube by 3 pi by r1 square minus r2 square. Let us take it this way, okay, which will be said as 4 by 3 pi of r1 cube minus r2 cube divided by r1 square minus r2 square. We will retain this equation. We will call this equation number 1, which is y bar 1, which is also equal to y bar 2 instantaneously. So, we can find quickly the ZP value, which will be a by 2 of y bar 1 plus y bar 2, which will be pi by 2 r1 square minus r2 square of 4 by 3 pi r1 cube minus r2 cube by r1 square minus R2 square, which gets simplified to 4 by 3 of R1 cube minus R2 cube. So, that is my ZP. Okay. Let us now quickly find out Iz, because we need to find Iz as well. Iz will be pi by 64 D14 minus D24 which will be pi by 64 2R1 4 minus 2R2 4 okay, which will become pi by 4 of R1 4 minus R2 4. Okay. So, I can now find Z equivalent as I by Y max, which will be pi by 4 of R1 4 R2 4 1 by R1, because Y max is actually R1, is it not, which will now become pi by 4 R1 R1 4 minus R2 4. So, I can now quickly find the shape factor as Zp by Ze. Let us say equation, this we call as equation number 3. So, I should say now this is equal to equation 2 by equation 3. So, which you simplify, which will be 4 by 3 R1 cube minus R2 cube, okay, divided by 4 R1 by pi times of R1 4 R2 4, okay, which will become 16 R1 by 3 pi of R1 cube minus R2 cube by R1 4 R2 4, right. Now, let R2 by R1 be a ratio K, okay. Then shape factor S was actually equal to 16 R1 by 3 pi of R1 cube minus R2 cube by R1 4 minus R2 4, which will be replaced as 16 R1 by 3 pi of R1 cube minus K cube R1 cube divided by R1 4 minus K4 R1 4, right, which will now become 16 by 3 pi, because R1 will all get cancelled, 1 minus K cube by 1 minus K4, okay. So, shape factor is given by 16 by 3 pi 1 minus K cube 1 minus K4, where K is the ratio of the radii, okay. Yes, interestingly friends, by substituting R2 equals 0, okay, this will reduce to solid circular tube, is it not? So, therefore, the shape factor S for a solid tube is 16 by 3 pi which we already have. Okay, so we landed up in the same equation, same as derived earlier. Okay. So, we have a very interesting example of a solid section and an annular section, right. Let us do one more example, as you see in the figure, which is a channel section, because these are common sections used in steel design. So, we are trying to work out the shape factors for all of them, so the design becomes easy and can handle it comfortably. So, look at the section available on the screen now. Let us say this dimension, the overall size is 200 mm. Okay. And the thickness is 5 millimeters, thickness is 5 millimeters through and through, right. Let us try to find out the total area of cross section. You can see this is going to be, I have divided like this. This is my first piece, okay. This is my second piece, and my third piece. So, which is going to be now 100 into 5, there are 2 such pieces, plus 200 minus 10, so 190 into 5. So, the total area becomes 1950. Since the section is symmetrical, equal area axis passes through the CG. Okay. One can easily find out y bar, which can be sigma A y bar by sigma A. We will try to find out. Look at this figure B here. So, that is going to be 100 into 5, okay, into 97.5, that is the CG of this piece, right. 100 into 5, 97.5, because this is 100 from here till here, it is 100. So, now this will not be, so from the CG to here, this will be 97.5 plus, then the second piece is this, which is 95 into 5, that is the area of this piece, and CG will be 95 by 2, okay, divided by total area 100 into 5 plus 95 into 5. If you work it out, you get this value as 73.14, which is y bar, which is indicated here. Now, I can work out ZP, which is A by 2 y bar 1 plus y bar 2. Area is already there. So, I can simply say it is 1950 by 2, 73.14 into 2, because y bar 1 and y bar 2 are identical. So, if you do that, I will get this value as 142 623 mm3. Let us try to find out the IZ value of this channel section. We can use parallel axis theorem. Okay. So, let us do that. 100 into 5 cube by 12 plus 100 into 5 into 97.5 square, that is my first piece. I have two such pieces plus these are for the flanges. Now, for the web going to be 5 into 190 cube by 12. You know, if this is 200, this will be 190, am I right? Because the thickness is 5 in both cases. Okay. So, if I make the total of IZ, this becomes 12.366 into 10 power 6. I can find Z elastic, which is IZ by Y max, which will be 12.366 into 10 power 6 divided by 100, that is the Y max, this is the extreme fiber from the neutral axis, which will be 12.366 into 10 power 4 mm3. So, I have Zp, I have Ze. Can I quickly find the shape factor? So, the shape factor will be now equal to Zp by Ze, which will be, can work it out, 1.153. Okay, friends. So, very simple example which is easily understandable. Let us do one more section, a T section. The dimensions of T are given 150 and the overall depth is 100 mm. Thickness of the flange and the web are different in this case. Flange is 5 mm, whereas web is thicker, 10 mm. Okay. Now, in this case, the first step is to locate the equilibria axis. In the previous example, this problem was not there because there was an axis of symmetry. In this case, of course, you have vertical axis of symmetry, there is no doubt. You have vertical axis of symmetry, but I want to find what would be this value. Okay. So, we would like to locate this, right. So, the first job is to find out the equilibria axis. So, let us divide this into two parts. Let us say this is my first piece and this is my second piece. Considering these two areas has got to be equal because the equilibria axis, no. So, let us find out area of the flange, which is 150 into 5. Okay. Let us find out area of the web, which is 95 into 10, which is 950. So, area of the web is more than the flange. So, therefore, the equilibrium axis has to lie at a distance y bar down into the web. So, we have to find out this distance y bar now, which is measured from the, okay, let us mark y bar like this, not here, let us mark y bar here. Let us mark y bar, which is going to be from the flange web junction. Let us say this is my y bar. Okay, let us do this. So, let y bar be measured from the intersection of flange and web. So, I can now say A by 2, which will be the total area, which is 750 plus 950 by 2, which is 1700 by 2, which is 850, and that should be equal to area of the flange plus 10 times of y bar. Am I right? Look at this figure. Okay. So, I have this, the governing equation I have. Area of the flange I know, which is 850 is equal to 750 plus 10 times of y bar, which will be telling me that y bar is 10 mm. Okay. So, at 10 mm from here, I locate the equilibrium axis. So, I have located the equilibrium axis. Okay. One can also check A1 going to be area of the flange plus 10 into 10, because I am working out this area, which is 750 plus 100, which is 850, which is exactly equal to A by 2 as you see here. Okay. So, it is okay. Now, I want to locate the CG of both the sections. Now, step number 2 will be to locate the CGs y bar 1 and y bar 2 of upper and lower sections. So, look at the figure B. So, two sections are drawn separately. Let us try to find out and apply this equation. So, y bar in sense will be A y bar by sigma A. Let us apply this and try to find out for y bar 1 first. So, let us say y bar 1 will be 150 into 5 into 12.5 plus 10 into 10 into 5 divided by 850, which is 11.62. So, it will be lying in the flange, okay, as marked in the figure. Let us do y bar 2. Y bar 2 will be, this dimension the total is 95, you lost 10 there, so it is 85. Y bar 2 will be 85 by 2, am I right? This is 85, which is 42.5. So, can I quickly find ZP? ZP is A by 2 Y bar 1 plus Y bar 2, which is 850 of 11.62 plus 42.5. So, ZP is 46002 mm. Okay, we got ZP. Let me find ZE. We know ZE is actually equal to Iz by Y max. Let us now consider the full T section. Okay. Now, to locate the CG of the T section. So, let us say the CG is taken as Y bar in this case. So, Y bar is sigma A Y bar by sigma A. Let us do it for two sections separately. So, 150 into 5 into 2.5 plus 95 into 10 into 95 by 2 plus 5. Right, divided by 1700, that is the total area. So, if you work out this, Y bar will become 30.4 millimeters, which is indicated here. So, now let us find out the moment of inertia of the section about the z axis, which will be using parallel axis theorem. Which can be said as B dq by 12 for the first piece plus 150 into 5 into 30.44 minus 2.5 the whole square, that is for the first piece. Do it for the second piece, 10 into 95 cube by 12 plus 95 into 10 into 52.5 minus 30.44. How do you get this 52.5? It is exactly this. Okay. So, can I find out this, which will be 1.767 10 power 6. So, now I can find ZE, which is I by Y max, which will be 1.767 10 power 6 by Y max will be 100 minus 30.44, because this dimension is 30.44 and this value will be 100 minus 30.44. So, substitute that here, I got 25402.5. This should be Y max, remember that friends, this is Y max. So, now I have ZE with me. So, can I find the shape factor? Shape factor S will be ZP by ZE which will be 1.767 10 power 6, that is my ZP which is here. Sorry, ZP will be 46002 divided by 25402.5, which will be 1.81, pretty high number, okay, 1.81. We will do one more example for an L section. Let us say the L section, the dimensions are given on the screen. The overall thickness is same, which is 5 millimeters. So, let us first locate the centroidal axis of this. It is an unequal angle. So, it has no axis of symmetry. So, we need to find out the equilibria axis and the CG both. So, let us find out the area of the shorter arm. The area of the shorter arm is 60 into 5. The area of the longer arm is 95 into 5. The total area is 775 mm square. So, now let us locate the equal area axis first. Let the equal area axis be at a distance y from the intersection face as shown in the figure, okay, y. So, we know that 60 into 5 plus 5 into y, okay, should be equal to 775 by 2. By this logic, y will become 17.5 millimeters. So, y will now become 17.5 millimeters. We can check also. So, A1 plus 17.5 into 5 should be equal to 300. We will call this as A1 and this as A2. Okay, total area is A1 plus A2. So, A1 plus 17.5 into 5, which is 87.5, which is 387.5 mm square, is actually equal to 775 by 2. So, it is okay, is it not? So, we have located now the equilibria axis. Now, our job is to locate the centroid of upper and lower areas. So, let us look at figure B. So, I want to find the centroid of the upper part, centroid of lower part, then I should find out the ZP, right. So, let us take the upper part, let us find out the lower part. Let us take the lower part. So, we will apply this equation sigma A y bar by sigma A. So, we get y1 bar as, remember this value was 17.5, am I right? And this is 5. Okay. So, y bar 1 will be 60 into 5 into 17.5 plus 2.5, okay, that is one piece, plus 17.5 into 5 into 17.5 by 2, that is the second one, divided by 387.5, that is the A by 2 value. So, that gives me 17.46 m. Okay, 17.46 mm is y bar 1, which is very close to the intersection, right, the 17.5 and this is 17.46. Let us work out y bar 2. Y bar 2 is very simple because we know the overall dimension. So, this is going to be 77.5 by 2, which is 38.75 mm. So, can you quickly find ZP, friends, using this equation, which is A by 2 y bar 1 plus y bar 2, which is 775 by 2, 17.46 plus 38.75, which will become 21781.38 mm cube. So, similarly, one can locate the CG. Okay, I am not giving the answer, I am not giving the procedure, I think you should be able to work it out. Use sigma A y bar by sigma A and you will get y bar as 33.15 m. Once I get y bar, I can find Iz, which will be 60 into 5 cube by 12 plus 60 into 5 into 33.15 minus 2.5 square, that is for the first piece, the short arm, and the longer arm. The longer arm, which will be 8.175 10 power 5 mm to the power 4. Zd is I by y max, which will be this value divided by 100 minus 33.15, which will become 12228.87 mm cube. Therefore, shape factor will now become Zp by Ze, which is 1.78. So, friends, in this lecture we learnt the shape factor calculations for rectangular section, solid cylinder, tubular member, L section, T section, and we learnt that shape factor varies with the geometry. It is not same, right. The maximum value of the shape factor is about 2.0, which is for a diamond section. You can try and find out. Okay. So, shape factor is a geometric property, and if I know shape factor, I can easily find the capacity of the section, which is very simple to find out from the derivations what we discussed in the last lectures. Okay. Thank you very much. Have a good day. Bye.